Now we're going to move on to the second part of integration. Like integration of exponential functions, this is also very simple, and it depends on your knowledge of the fact that integration is the antiderivative. So again, if you don't know what trigonometric functions is, then you're way too late. But as you know, trigonometric functions are ones that basically depend on sine, cosine, and tangent as a basic, and then there's also uh, cosecant, there is secant, and there is cotan. Those are like trigonometric functions, and of course you remember that whenever we talk about trigonometric functions, we should always remember the trigonometric identities, like sine squared x plus cosine squared x equal 1. That's our this is one of our most basic ones. You need to remember that 1 plus tan squared x is going to equal to sec squared x. Uh, you need to remember technically every single trigonometric identity you ran across, not only for this chapter but for also for previous chapters that we mentioned in C4 and earlier. So yes, how do we integrate those trigonometric functions? We know what trigonometric functions are, we remember the identities. Now what? Well, simply let us start here by drawing a table. Our table is f of x and f prime of x. So we're differentiating really. It's very simple. So we know that if we differentiate sine x, we're going to get cosine x. We know that if we differentiate cosine x, we're going to get negative sine x. We also know that if we differentiate tan x, we're going to get sec squared x. And if we differentiate sec x itself, we're going to get sec x tan x. Oops. Sec x tan x. Now if we want to do cosecant instead, we're going to get negative cosecant x into cotan x. If we want to differentiate cotan x itself, we're going to get negative cosecant squared x. Those were the normal differentiations. Now, as we said, we remember that integration is the reverse of differentiation. In other words, if you want to differentiate cosine x, you're going to get sine x. If you want to differentiate sine x, you're going to get cosine x. Negative cosine x, sorry. Because here, if you differentiate negative sine x, you're going to get cosine x. Take the negative from here to there. And then if you want to differentiate sec squared, you're going to get tan. If you want to differentiate sec x tan x, you're going to get sec x, etc, etc, etc. Now, how about the things we don't have on the right side? How do we go from there to there? So, well, again, those are things you get to know throughout the chapters, things you figure out that you need to use, etc. For example, but instead, if I gave you this example and it's not from the table, so if I told you to integrate tan squared x dx. Now, we know if we go back to our table and we want to look to our right, we have not a thing with tan squared. And even with differentiation, we don't have it except if we do it with the chain rule. So what do? In case we don't know, the first thing that crosses our mind is, why don't we use trigonometric identities? Do we have any identity to do with tan x squared x? Yes, we do. So what we're going to do is that we're going to change this into 1, actually sec squared x minus 1 dx. Now, as we know, when we have a minus or plus, we can simply divide it into two integrals. So this will be sec squared x dx minus dx itself, or 1 into dx. And because we know the rules of integration, we know from our table that if we have sec squared x, which is right here, we can, in other words, this will be tan x, and here it's like 1 into x to the power 0. We're going to add 1 to the power and divide by 1, which means we're going to have minus x plus z. And you can then, from here on, you can memorize how to differentiate this, and it will be completely and very easy and simple. And that would be the example on trigonometric identities. Anything from then on can be done this way. You can just depend on the rules, because actually this table of from um, the differentiation does not only apply to trigonometric identities. For instance, we said that if we differentiate ln x, we're going to get 1 over x, which means that now in every integration where we have 1 over x, we can change it back to ln x. And this applies also to many other formulas, like just we did with the exponential function, and just what like we're going to continue doing in so many places. Now I need you also to take in consideration the example where the subject is not just x. For instance, here if I told you I want you to find to integrate for me sine of 5x dx. What you're going to do is that you're going to simply integrate sine, as we said to our table. We know that sine will give us negative cosine, because negative cosine will be differentiated into sine. And we keep the subject as is. But we don't stop here. We have to divide by the differentiation of the subject, just like we did with the exponential function. And then we add our c. In order to check our answer, we are going to differentiate back. And we said that differentiating negative cosine will give us sine. We keep the subject as is, and this is divided by 5. Now we're going to multiply, because this is differentiation, by the differential of the inside function, and this will give us 5. And c will be differentiated to 0, and then our 5's can be cancelled out, and we will be left back with the actual given question, and that in this way we'll be sure that our integration was actually correct, and we know how to integrate trigonometric functions simply and easily.